Good morning, everybody. So it's the discussion, and today I have a couple of different topics to talk about. Want to talk about selective reduction and synthesis of carboxylic acids, and also uh, get into some acyl substitution. Okay, first up, let's talk about selective reduction. So remember, reduction means more bonds to hydrogen. An atom that is undergoing reduction is gaining more bonds to hydrogen or fewer bonds to oxygen. We have a couple of different reagents that accomplish reduction. All right, so first of all, we have, so this is reducing agents. And we have three. First up, we have hydrogen and a metal catalyst, platinum or palladium or nickel. There are various metal catalysts that we can use for with reduction with hydrogen. But what I really want to stress is that the hydrogen, this reduces this reduces alkenes, alkynes, aldehydes, ketones, and imines. Okay, then our next reducing agent is sodium borohydride, and it's less reactive little brother, sodium cyanoborohydride. Okay, so this is a mild reducing agent. It doesn't reduce alkenes, it doesn't reduce alkynes, but it does reduce aldehydes, ketones, and imines. Okay, our third reducing agent is lithium aluminum hydride. And this is a very reactive reducing agent. This thing reduces practically everything. It reduces aldehydes, ketones, imines, esters, carboxylic acids, nitriles, amides, epoxides, nitro compounds, blah, 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 on and on. Lithium aluminum hydride is extremely reactive, and so it's going to reduce all of these functional groups. And it does so with little selectivity. So that if you have a molecule that has an aldehyde and an amide in there, it's going to reduce both of them. If you have a molecule that has any two of these functional groups, it's going to just reduce everything. So that you have to be cunning when you use lithium aluminum hydride, because you have to make sure that the reagent is not being offered a choice of what to reduce. Okay, so so this is a summary of the three reducing agents and what they reduce. Let me just make another little point here about these reductions, and that is about selectivity. Okay, for hydrogen and a catalyst, one thing that we can definitively say is that an alkene is reduced faster than an alkyne. And then the alkyne is reduced faster than the aldehyde and ketone. But with lithium aluminum hydride, the executive statement here must be no selectivity. You can't have, as I said before, you can't have a molecule that has an aldehyde, a ketone, an ester in it and expect just the ester to be reduced or just the ketone to be reduced. Lithium aluminum hydride reduces all kinds of stuff with very little selectivity. Okay, so let's do a problem where we're employing these principles. So if we have this compound, and we can do, so we have a carboxylic acid, we have an alkene, and we have a ketone. Okay, so let's imagine reducing this with lithium aluminum hydride, and then some kind of aqueous workup. We can use water or we can use H2O, H3O plus. And now let's reduce this very same compound with sodium borohydride. And the traditional solvent to use here is methanol, right? That's just the solvent. If you ever see sodium borohydride and above the arrow and CH3 below the arrow, that means the CH3OH. That is the solvent. And then we could also try reducing this compound with hydrogen and a metal catalyst. I'm going to put palladium, but we could use platinum and all kinds of other compounds. Okay, so I'm going to give you a minute and let's try, first of all, let's see what is going to happen with reduction of with hydrogen. This is easier. Okay, so, and also let me just point out that this would be excess. Let's see what happens. So take some time, look at the previous board that I had, and maybe you can see, maybe you were taking notes, maybe you can predict the product. Okay, so give you some time to try to figure out what's going to happen with this reduction with hydrogen. So we're doing this one first. Okay, so hydrogen, so there's a carboxylic acid. Hydrogen doesn't reduce a carboxylic acid. There's an alkene. Hydrogen reduces an alkene. There's a ketone. Hydrogen also reduces an alkene. But we made the point that an alkene is reduced faster than an alkyne, and an alkyne is reduced faster than an aldehyde or a ketone. Okay, so with the first thing that's going to be reduced is going to be the alkene gets reduced to an alkane. Right? Remember, reduction means more bonds to hydrogen. So that this carbon here in the original starting material, each of these carbons start life with one hydrogen, but then they undergo this reduction, and those carbons now have two hydrogens. So this is the hallmark of reduction, more bonds to hydrogen. Okay, but now since we have excess hydrogen, the second equivalent of hydrogen is going to reduce the ketone to an alcohol. All right, so we will get carboxylic acid up here. And now just like this carbon-carbon double bond was taken down to a carbon-carbon single bond with hydrogen added across where the carbon-carbon double bond used to be, very same thing is going to happen down here with the ketone. The carbon-oxygen double bond will be taken down to a carbon-oxygen single bond, and hydrogen will add across where that carbon-oxygen double bond used to be. So I could put a hydrogen there, and I could put a hydrogen there as well. Okay, so that's going to be the reduction product with hydrogen. Okay, now let's try this reduction with sodium borohydride. And maybe take a few minutes. Maybe you were taking notes and you got my comments about what sodium borohydride reduces. So let's take a few minutes. Let's draw the structure of the product with special emphasis placed on how the product we're going to write here, does it or does it not differ from the product of reduction with hydrogen? Okay, so there's a carboxylic acid. Sodium borohydride doesn't reduce carboxylic acids. There's an alkene. Sodium borohydride doesn't reduce an alkene. There's a ketone. Sodium borohydride does reduce ketones. It reduces ketones, aldehydes, and imines. And so the product here is going to be different from the product of reduction with hydrogen. So what we are going to get here is nothing happens to the carboxylic acid. So that just stays the same. Nothing happens to the alkene. So that just gets carried over. But the ketone is reduced to an alcohol, where the it's similar to, it's just as if you get the same result as reduction with hydrogen, insofar as the carbon-oxygen double bond adds hydrogen, the atoms of hydrogen across where that double bond used to be. So see, if you reduce this compound with hydrogen, you're going to get something different from reduction with sodium borohydride. Okay, the much more complicated is this reduction with lithium aluminum hydride. Lithium aluminum hydride reduces all kinds of stuff, all kinds of functional groups. So the carboxylic acid will be reduced to an alcohol. And was that the addition of more hydrogen? Oh my heavens, yes. The carboxylic acid carbon starts life with 0 bonds to hydrogen, but in the product, now it has 2 bonds to hydrogen. And as I said before, that is a hallmark of reduction. Lithium aluminum hydride doesn't reduce an alkene, so the alkene just sticks around. Does lithium aluminum hydride reduce a ketone? It does. And so here we're going to get a we're going to get a secondary alcohol, where again, this ketone carbon gained more hydrogen. It starts life with 0 bonds to hydrogen. Now in the product, it has 1. So we see here that we get 3 different substances depending on what the reducing agent is. Okay, so that's just some just a sample problem showing how the different reducing agents have different effects. All right, now let's talk about some reactions that involve synthesis of carboxylic acids. Okay, and so some older chemistry that we've already dealt with, let me just review that for you. We have a couple of different ways. One way would be to take a primary alcohol and react that with the Jones reagent. That's chromium trioxide, H2SO4, and water. And so this primary alcohol is oxidized to a carboxylic acid. So this is chemistry that we encountered a long time ago. And just like reduction means more bonds to hydrogen, oxidation means fewer bonds to hydrogen or more bonds to oxygen. The primary alcohol carbon starts life with 1 bond to oxygen, and in the product now it has 3 bonds to oxygen. So that's an oxidation. That's one of the hallmarks of oxidation. Okay, another method for carboxylic acid production would be the oxidation of an aldehyde. Once again, using the Jones reagent, chromium trioxide, sulfuric acid, and water. And this also is going to produce a carboxylic acid. And once again, we see oxidation in the works here. This aldehyde carbon starts life with 2 bonds to oxygen. Now in the final product, it has 3 bonds to oxygen. That's a hallmark of oxidation. Okay, a couple of more methods for oxidation, for production of a carboxylic acid, and that would be Tollens oxidation. This is a reaction of an aldehyde, and so we use silver ion, and so the most popular reagent here is that silver ammonium complex, right? And the conditions are basic, and so the aldehyde is oxidized to a carboxylate, right? And so why is that an O minus? Well, these are basic conditions. And you know, whenever you see a negative charge on an oxygen atom, you know that that's a base. So it makes sense that under these basic conditions, you're going to get this carboxylate. Okay, but we ordinarily don't want the carboxylate. We want the carboxylic acid. So there would have to be a separate workup step with aqueous acid. And what this workup step does is it protonates this O minus, and that makes the carboxylic acid that we're looking for. Okay, more methods for synthesis of carboxylic acids. Another method would be carbonation of a Grignard reagent. So we start out with an organic halide, react that with magnesium. That makes the by now very familiar Grignard reagent. And then the Grignard reagent is allowed to react with carbon dioxide. And we know that the Grignard reagent, this is sort of like R minus MgX plus. It behaves as if that's what it was. And so this R minus comes in, it attacks the carbon of carbon dioxide. You know that Grignard reagents attack carbonyls. Well, carbon dioxide is a carbonyl on the left and carbonyl on the right, or it looks like that anyway. And so we would get this carboxylate. And then there's a separate workup step in which we treat this carboxylate with aqueous acid. So this is nothing new. Whenever we run a Grignard reaction, we always have this acid workup. And so there is the carboxylic acid that we're looking for. All right, so one of the things I'd like to point out about this procedure here, the carbonation of a Grignard, is that the carboxylic acid that we get here has one extra carbon from the organic starting material we started with here. So that's different from what happened in 1, 2, and 3. We didn't add any extra carbons. So that carbon got oxidized, that carbon got oxidized, that carbon got oxidized. But here we've added one extra carbon. The carboxylic acid carbon was not present in the organic halide that we started with to make the Grignard reagent. So this is one way that it's different from one way that carbonation of a Grignard is different from these other methods. And there are more methods for creating a carboxylic acid. I don't think we've gotten to them in the lecture yet, but can't really remember. So let me just point out here that another method that we would have would be hydrolysis under acidic conditions or basic conditions of a nitrile. So here we would add H3O plus and heat, or we could also do this under basic conditions, OH minus H2O. That would be our first step, and then we would have, because those are basic conditions, then we would have another step with an aqueous workup. But here what we're going to get is the nitrile carbon is converted to the carboxylic acid carbon. So we have lots of methods for making a carboxylic acid. This is just a summary of the various methods. Okay, so let's try a synthesis problem. So something simple to start out with. What about synthesize this guy, this alcohol, from, you can use any starting material you would like, but it has to contain 4 carbons or fewer. Okay, well, we're talking about synthesis of carboxylic acids, but that target molecule is not a carboxylic acid, it's an alcohol. That notwithstanding, we can create this compound by using a little bit of cunning and coming up with a synthesis that involves a carboxylic acid. Okay, so as usual, we do these synthesis problems retrosynthetically. This is an alcohol. We have bazillions of ways of making an alcohol. But the method that I'm looking for here is, we know that lithium aluminum hydride will reduce a carboxylic acid to an alcohol. That's one of the reactions that we talked about a few minutes ago. So that although we would have bazillions of ways of making this, what I want to show is how we can use our carboxylic acid chemistry to synthesize this molecule. All right, so it's an alcohol, and we know that we can reduce a carboxylic acid to an alcohol using lithium aluminum hydride. So this alcohol could be synthesized by reducing this carboxylic acid to an alcohol. Okay, and so now this becomes our new target in our retrosynthetic plan. And so how many carbons in this guy here? 1, 2, 3, 4, 5. It's too big because our restriction is that our starting materials must have 4 or fewer carbon atoms. Okay, now is this restriction just something that you would see on a test? Not at all. Because it turns out that the more carbons a compound has, the more expensive it is. This is a real world consideration. The more expensive it is, and the more unlikely it is to find it in the Chemicals Are Us catalog. So when we're making molecules, ordinarily we want to start with something that is small because that is going to be inexpensive, that is going to be commercially available. Okay, so this restriction here has some real world considerations. Okay, so this is a carboxylic acid, and we just talked about all of the various ways of making a carboxylic acid. One of them would be carbonation of a Grignard. And we said that when we use that reaction, the carbon dioxide carbon becomes the carboxylic acid carbon, and the Grignard reagent has as many carbons as the target minus 1. Okay, so this guy could be synthesized by reacting the Grignard reagent that looks like this. Oh, so that's now a legal compound. And where did the 5th carbon come from? I'm going to put a dot on him. Where did that 5th carbon come from? That came from the carbon dioxide, right? I'm going to put a little dot on him, and then followed by aqueous workup, aqueous acid workup. Okay, so that would be our synthesis of this carboxylic acid using carbonation of a Grignard. We could take this, we could walk this back further because we know how to make a Grignard reagent. Are you thinking about how to make a Grignard reagent? All right, that would be the insertion of magnesium between the organic group and the halogen. Okay, and so this is also a legal compound. This also fits our restriction here because this has 1, 2, 3, 4 carbons, so it would be considered a legal compound for the synthesis. Okay, So let's try something now a little bit more challenging. And that would be the synthesis of this carboxylic acid. Okay, this is the drug Depakote. Depakote is an anti-mania drug. Maybe you know about bipolar personality disorder, which is the patient has experiences episodes of depression as well as episodes of mania. There are lots and lots of drugs that deal with depression, but there are very few drugs that deal with the mania. Mania is a psychosis. Uh, Someone with that is going through a manic episode is going to want to do something like stay awake for 3 days, or go out on a shopping spree and max out all of their credit cards buying 5 mink coats that they don't need, or two Lexuses or something like that. It's a very serious psychosis. So that's what mania is. There aren't very many drugs that can deal with the manic side of bipolar disorder. So let's try to synthesize this guy. And again, let's have this real world restriction. Synthesize him from C4 or smaller. All right. So it's a carboxylic acid. We know a couple of different methods for making a carboxylic acid. So beginning our retrosynthesis here, we could try carbonation of a Grignard, or we could try various other procedures. So let's try carbonation of a Grignard, where the carboxylic acid carbon came from carbon dioxide. And so the required Grignard reagent that we would need would be maybe something like that. I could put Br there. I could also put Cl there. Okay, so that's going to put in that carboxylic acid functionality. Okay, how about this guy? 1, 2, 3, 4, 5, 6, 7 carbons. It's too big. It's probably not available at Chemicals R Us. So we're going to have to make it in the laboratory. So how do we make a Grignard? The retrosynthetic step here would be the insertion of magnesium between the organic group and the halogen. So we would need this alkyl chloride as the starting material to make this Grignard. Okay, but now this is still too big because it still has 7 carbons. It's still too big. We need to chop it up. So how do we put Cl on stuff? Remember how to put Cl on stuff? Orgo 2 style? Darzens halogenation would be a very good way. Thionyl chloride and pyridine. But that is a reaction of an alcohol. Okay, so now this is our new target, but it's still too big because it still has 7 carbons in it. So we're going to have to make this guy as well. All right, now it's once again, it's an alcohol, and we have a bazillions of ways of making an alcohol. Right now, all we want to do is make this alcohol from something that has 4 or fewer carbon atoms. So how about another Grignard reaction, right? When we could make this using another Grignard reaction, where we would take this aldehyde Oh, and he's legal. 1, 2, 3, 4 carbons. He's legal. And we're going to bring in the right-hand part of this molecule using a Grignard. So maybe something like this propyl, normal propyl magnesium chloride, then H3O plus workup. Okay, and so when we react an aldehyde or a ketone with a Grignard reagent, we get an alcohol where the alcoholic carbon, this guy right here, I'm going to put a dot on him, the alcoholic carbon, the alcoholic carbon now has is converted has the Grignard reagent attack this carbonyl carbon, made this alcohol, and we can see this 3 carbon unit over here. Okay, so he's legal. We know how to make an aldehyde, but he's also legal. And so we wouldn't have to necessarily make him. He's probably commercially available. But just in case we had to make him, we could also use more Grignard technology and start out with 1-chloropropane. Okay, so that would be our synthesis of Depakote from these small molecules. All right.